This is Professor Doherty, and today I will be going through the third lecture on the respiratory system. And today what we're going to be covering is transport of gas, and so specifically we're going to talk about carbon dioxide since we covered oxygen transport last time. And then that nicely leads into the acid-base balance of the blood because carbon dioxide has a heavy effect on the acid-base balance of the blood. And then we'll talk a little bit about hypoxia and what happens when you go to high altitudes. All right, so with that, let's go ahead and take a look at carbon dioxide transport. So I'm going to go to my drawing pad here. So in your cells, so let's imagine that you have a bunch of cells here. And these cells in your body, these can be any cells, so wherever. These cells are constantly going through metabolism, basically breaking down sugars and fats. And the byproduct of that is, of course, carbon dioxide. So let's give that a color here. How about blue? So these cells are all producing CO2. I'm not going to write it into all of them. And they need to get rid of this waste product. And somewhere near them is going to be a blood supply, so we'll put a blood supply here. Actually, I'll expand this out a little bit so I can draw a little bit more. So this is our blood supply flowing along here. And so what these cells do is obviously they're going to move this carbon dioxide out. Typically they will dump it into the extracellular fluid and then it will make its way into the blood. So all of this carbon dioxide winds up in the blood eventually. Now there's three ways that carbon dioxide is transported in the blood. So it's not as simple as what you might think. Some of the CO2, so about 10% of it, and let's go ahead and write this up here on top because this is kind of the point of this. 10% of the carbon dioxide produced by your cells will be transported away from the cells in blood plasma. So it's going to be transported in blood plasma. And that means it's going to be transported as a gas. And so, for instance, here, this CO2, let's say that this is about 10% of our total production of CO2 is going to be in the plasma. So it's basically just in the fluid in the blood as a gas. All right, so some of the CO2, well, obviously there's another 90% that we have to deal with, is not going to be transported in the plasma. And that portion of it is going to be transported or dealt with in some way actually by the red blood cells themselves. So let's make some rather large red blood cells here. So these are red blood cells, oversized a little bit. And so I'll put a little dash around them to show the red blood cells. And let's draw another one real quick here too. Ooh, there we go. Not my prettiest drawing, but whatever. Some of the CO2, so let's bring the CO2 here, is going to go into the red blood cell itself. Okay. Here, it's going to combine with hemoglobin actually, which is a little, I don't know, to me it's a little unusual, but a lot of people believe this to be true for all carbon dioxide, but it's not. And this becomes carbaminohemoglobin. So hemoglobin combines with carbon dioxide here. Okay, and so let's add that up to the top up here, and that comes out to be about 20% of total carbon dioxide produced is transported this way. So we can add that up here to the top of our screen. Let me bring that back over. And we can say that 20% of our CO2 production is going to be transported away in a form called carbaminohemoglobin. Carbaminohemoglobin. So carbaminohemoglobin is just basically hemoglobin bound to carbon dioxide. Okay, it has a strange name, implying an amino acid in there or something, but it's carb amino hemoglobin is this down here that I drew. Okay, it's carried inside the red blood cell, so this carbon dioxide goes inside the red blood cell, combines with hemoglobin, and gets transported in that fashion and in that form. The final 70% here, so actually let me get rid of some of this arrows here. I'm going to change this a little bit so that it's this arrow coming out. The final 70% of hemoglobin, or excuse me, carbon dioxide, goes into red blood cells and gets changed, so 70% here of this carbon dioxide gets changed into bicarbonate, so HCO3 minus. So if we go up here, the final 70% of carbon dioxide is transported as bicarbonate. Now, in order to get turned into bicarbonate, it has to go through the bicarbonate equation, if you recall. So if you remember the bicarbonate equation, I'm going to write down here is carbon dioxide plus water. Can go either way here, but it's going to push in this direction, becomes carbonic acid. And then this will then split into hydrogen ions plus bicarbonate. Sorry, I ran out of room here. HCO3 minus, this is bicarbonate. So this is where 70% of the carbon dioxide that's produced in the blood will wind up going into this system. And notice it gets turned, so here you can find the CO2 here, right? So here's where the CO2 is. It's now bound in carbonic acid, and then eventually our CO2 winds up being part of bicarbonate. So essentially our CO2 is bound as bicarbonate, and that's what you're seeing over here in this red blood cell. Okay, now this bicarbonate does not stay in the red blood cell. It will come out of it, and let's go ahead and talk about that next. Okay, but you should be aware of these numbers as far as how carbon dioxide is going to be transported. Okay, so now let's take a look at what happens for the transport of that bicarbonate. Okay, so here we have our blood system here again, and here we have a red blood cell, and here we have CO2 being produced that's going to go into the red blood cell. Okay, now here of course our CO2 goes through changes. It's going to combine with water inside the red blood cell, so we're going to go through our bicarbonate equation. So we're going to get this CO2 combines with water, that becomes carbonic acid, and then that in turn is going to split and become hydrogen ions, and I'm going to make this blue here so we can see it, or actually green, and bicarbonate, HCO3 minus. Okay, so basically now our carbon dioxide is now bound as bicarbonate. Well, that bicarbonate, we don't want to leave that in the red blood cell. We need to get it out into the blood plasma. So remember, out here we have blood plasma, right, along with the red blood cells. So in order to get this bicarbonate out of the red blood cell, something happens called the chloride shift. And so you should be aware of this also. Basically, in order to get the bicarbonate out of the red blood cell, we have to exchange it for something. And in this case, we're going to exchange it for chloride. So there are chloride molecules that are out floating in the blood plasma. And what they do is they will exchange into the red blood cell. I'm just changing the color because I don't feel like changing it back. In exchange for bicarbonate getting out of the red blood cell. And this is important because the bicarbonate out here, so this is bicarbonate now, is a very important blood buffer. So it's good at buffering free hydrogen ions. In other words, it's good at keeping the pH of the blood steady. Remember, our normal blood pH is approximately 7.4, and basically bicarbonate helps to stabilize that. So this is an important exchange, this chloride shift. This chloride shift happens at the level of the cells, so it happens in the tissues, or I should say around the tissues, right? So in the blood around the tissues, so I don't confuse people. So in other words, here, what's creating all this carbon dioxide are cells. Maybe these are liver cells that are creating all this carbon dioxide. So this chloride shift that's happening here, right, that's taking place here, is taking place at the cells of the body. So not at the lungs. So I'm trying to make that clear. It's happening at the cells. That's where this chloride shift happens. Okay. All right. Now, let's go back. I'm going to clear this off, and we're going to take a look at a couple slides. So that's the chloride shift and what happens with carbon dioxide. Okay, so just a few slides on this. Carbon dioxide gets released from the tissues, and this is just reiterating what we just went over. 70% of that carbon dioxide is going to wind up as bicarbonate in the blood for transport. 20% is going to wind up as carbaminohemoglobin, so bound to hemoglobin in the blood, and 10% will get dissolved as a gas, and that contributes to the partial pressure of carbon dioxide in the blood, is just this 10%. Now, one thing I do want you to make a note of is that carbon dioxide bound to hemoglobin is called carbaminohemoglobin, not carboxyhemoglobin, because that's an easy mistake to make. If I leave this recording the same, you noticed I almost made that mistake when I began talking about it. So carbaminohemoglobin is carbon dioxide bound to hemoglobin. Carboxyhemoglobin, so go ahead and write this down as well, is when carbon monoxide is bound to hemoglobin, and that is deadly. So carbon monoxide, it has a formula of CO. That's carbon monoxide. Carbon dioxide, which is what we're trying to get rid of up here, right, is CO2. This stuff, carbon monoxide, as many of you are probably aware, is deadly. It has a tendency to stick to hemoglobin extremely strongly. So carboxyhemoglobin is incredibly bad. Carbon monoxide will actually stick to red blood cells about 238 times stronger than carbon dioxide will. So it really grabs a hold of hemoglobin. Okay, here is the bicarbonate equation, just again in another form here, that happens during the chloride shift, and I already described the chloride shift, where chloride shifts into red blood cells in exchange to get bicarbonate out, so that bicarbonate can be in the blood plasma to deal with any changes in pH. Now, that creates a problem though, and that is that we need to get carbon dioxide back out of the bicarbonate when we get to the lungs. And so that brings us to what's called the reverse chloride shift. So the reverse chloride shift, you should understand, takes place at the lungs, not at the level of the tissues like the chloride shift did. So notice the difference in the name here. This is the reverse chloride shift. Here's what happens, is basically just the reverse of what we did before. So now if you look at this picture, we're now at the lungs. You can see here are the alveoli. Here we have blood plasma down here with red blood cells. And look at what's happening. So here what's happening is the chloride that was inside of the cells is now moving out of the cells and back into the blood plasma in exchange for bicarbonate, which is going to move back into the red blood cells. Now, within the red blood cells, there is an enzyme called carbonic anhydrase, and this facilitates the ability of the bicarbonate equation to take place in either direction. In this case, since at the lungs here, we're now having a bunch of bicarbonate re-enter the red blood cells, what happens is it shifts everything in this direction. Okay, so you're going to have bicarbonate combining with hydrogen ions to make carbonic acid. Carbonic acid is then going to get broken back into carbon dioxide and water. Water really doesn't matter for us, but the carbon dioxide then is going to leave the red blood cells and eventually make its way back into the alveoli, where it can then be breathed out, right? So this carbon dioxide is then going to exit the body from the lungs. So remember, this is about 70% of your carbon dioxide that was transported as bicarbonate is now leaving the lungs by going through this this reverse chloride shift and then getting changed back from bicarbonate into carbon dioxide. Now, the same, or not the same thing, but the other carbon dioxide that's also in your system is also going to try to leave as well. So for instance, the carbon dioxide that's just sitting as gas in the blood plasma is also now leaving, right? And the carbon dioxide that's sitting attached to hemoglobin is now going to lose its affinity for hemoglobin, and it's also going to leave and try to get out through the lungs as well. All of this is taking place due to partial pressures. If you recall, the partial pressure of carbon dioxide in the blood is about 46 millimeters of mercury, right? And the partial pressure within the lungs at the base of the lungs down here is approximately 40 millimeters of mercury. So you can see that there's an overall push from high to low of carbon dioxide wanting to leave the blood. And this is all just due to partial pressure. Okay, so this was PCO2, right? Okay. I think I've written enough on this slide here. So that's how we transport carbon dioxide. Now that carbon dioxide contributes to the acid-base balance of our blood. So whenever you hear me speak about acid-base balance, I'm speaking about the acid-base balance of the blood, okay? And if you recall, there were two ways that we could really affect the acid-base balance of the blood. One was by what the lungs do, and the other is by metabolic means. Okay, that involves the kidneys as well as other cells in the body, all your other cells. In this case, we're going to focus on the lungs. Now, you've seen this slide before, so this is basically a reiteration because I want to emphasize this, that we have two ways that we can change the acidity of the blood from the lungs. One is by creating what we call respiratory acidosis. If you recall, respiratory acidosis is created when you go into a state of hypoventilation. Hypo meaning low, so low ventilation, so low breathing. This is basically the equivalent of holding your breath, is essentially what this is. So if you hold your breath, what's going to happen? Well, what's going to happen in regards to carbon dioxide, because that's what we're talking about here, because carbon dioxide is what affects the acid-base balance. Carbon dioxide is going to build up or accumulate in your tissues and therefore is going to accumulate in your blood. So holding your breath causes accumulation of carbon dioxide in your blood. And the reason why is because your cells of your body are still doing their normal metabolism, and that normal metabolism, the carbon dioxide as a waste product from it would normally be leaving, but now you're holding it in your system. This causes the partial pressure of carbon dioxide to increase in the blood. Now, this extra carbon dioxide, due to the bicarbonate equation, is going to cause a decrease in blood pH. So your blood pH is going down as your carbon dioxide levels go up. But along with this, that one thing that kind of offsets this though, so this is one of the good things about carbon dioxide, is it actually increases your bicarbonate levels because of that chloride shift that we just talked about. We're able to pull some of that bicarbonate out of the red blood cells, or most of it. So even though you're having problems with pH due to carbon dioxide, there is a little bit of offset to that. But still, the overall effect is that carbon dioxide is going to cause your blood to become acidic. Now, on the other side of that, you can cause the opposite effect, which is called respiratory alkalosis. This is typically due to hyperventilation. So cases of hyperventilation just means that hyper means a lot of, and then ventilation, breathing. So you're breathing too much, too rapidly. When you hyperventilate, you actually cause an excessive loss of carbon dioxide. So there's a balance in your blood of carbon dioxide, which most people aren't aware of. So basically your breathing is keeping up with your cellular metabolism in order to maintain a certain amount of carbon dioxide in your blood in order to maintain blood pH. You would think that by hyperventilating and getting rid of a waste product like carbon dioxide that you would be doing a good thing, maybe. But in fact, what happens is you throw the acid-base balance of your blood off and you put it towards the basic side, towards alkalosis. So when you're getting rid of carbon dioxide, you're actually getting rid of acid out of your blood, essentially. When you hyperventilate, this causes a decrease in the partial pressure of carbon dioxide within the blood. And of course, the overall volume of carbon dioxide decreasing causes an increase in your pH. Remember, an increase in pH is a move towards the alkaline side, also called the basic side, so however you want to think of it. And this, of course, the pH goes up as the protons are decreasing in amount in the blood, because that's what's really driving this pH change, is the protons. And this is all due to the bicarbonate equation, right? And as this happens, as your PO2 decreases, your blood plasma bicarbonate decreases. And remember, this is your blood buffer, so that doesn't help things either in this case. So you can see how by either breathing too much or too little, that you can actually throw your blood acid-base balance into disequilibrium and create problems for yourself. And of course, this can cause things like metabolic problems. The loss of oxygen, though, can also cause dizziness, as well as this acid-base problem as well. Okay, so here this picture just goes in to describe in a little more detail here the effect of bicarbonate on the blood, or at least it gives you a picture so that you can maybe understand a little bit better. Some of you, if you think about this, you might be asking yourself, well, if carbon dioxide is making carbonic acid, and we're getting one hydrogen off of that carbonic acid for every bicarbonate we're making, and those are winding up in the blood, then won't they just offset each other? How does bicarbonate benefit the blood in any way as a buffer if it's just being offset by its own hydrogen, right? And the reason why is because some of the hydrogen, if you remember, when I talked about carbon dioxide, this was true, but I haven't talked about this yet. Some of the free hydrogen will actually bind to hemoglobin and stay inside of the red blood cell. So when this chloride shift happens, which is shown here, where we're pulling bicarbonate out of the red blood cell and into the blood, you're actually getting more bicarbonate out of the red blood cell than you are hydrogen ions. And that allows the bicarbonate to serve as a buffer. Now, the bicarbonate is going to buffer metabolic acids that are being created. So, for instance, when you burn fats, you wind up making ketones, and ketones are non-volatile metabolic acids. They basically become anions. They pop off one of their hydrogens, and because of that, that actually increases the amount of acid that's in the blood. Well, bicarbonate can serve to offset that. Very simply put, that was kind of long-winded of me, but let me say it in another way. The extra bicarbonate that comes out of the red blood cells can offset metabolic acids. So it's just another source of acids that need to be buffered, basically. And all of that basically contributes to keeping blood pH steady at 7.4. Now, this has a number of important effects, and we talked about those effects on the on the oxyhemoglobin curve shown here. So if you recall, pH helps to set the oxyhemoglobin curve here. So how much oxygen is sticking to hemoglobin at any time, right? If you recall, as we become more acidic, so this line here over to the right at 7.2 pH, so remember these numbers are pH numbers, 7.2, we have more oxygen popping off of hemoglobin at the tissues, which is one of the benefits of getting slightly acidic blood as you exercise. If we go in the other direction to this line at pH 7.6, where it's becoming slightly alkaline, you can see that the oxyhemoglobin curve actually becomes a little bit worse. So remember that shifts down and to the right are beneficial for getting oxygen to tissues. Shifting this curve up and to the left has the opposite effect. It is not beneficial to tissues. Okay. Now this brings me to carbon monoxide, which we talked about before. Here is an image of or a drawing, rendering I should say, of a carbon monoxide molecule. One carbon molecule shown here in black and one oxygen shown here. Here is carbon dioxide. Again, carbon shown in black, oxygen shown in red. Carbon monoxide has a much, as I mentioned before, a much greater affinity for hemoglobin. And I think I mentioned it's about 230 or about 238 times stronger in how tightly it attaches to hemoglobin. Because of that, it doesn't let go of hemoglobin. And so it winds up actually shifting this curve, the oxyhemoglobin curve, over to the left quite severely if enough of it binds. Every time a carbon monoxide molecule binds to hemoglobin, it basically takes that hemoglobin molecule. So if we have a hemoglobin molecule here and this binds to it, it doesn't let go of it. And if it doesn't let go of it, then it basically knocks it out of existence. And so you can never use this hemoglobin again. It's gone once it's bound to carbon monoxide, essentially. Okay. Carbon monoxide is deadly because of this. But we should talk about where carbon monoxide is made. So carbon monoxide is primarily made from combustion engines. So any engine that burns a organic based fuel is probably going to produce carbon monoxide. So your car, if you're burning gasoline, if you have a gasoline car, it's going to produce some carbon monoxide. Wood burning stoves in your house will produce them. Furnaces. If there's a house fire, house fires produce carbon monoxide, and sometimes that can cause people to pass out. Cigarettes produce a bunch of carbon monoxide, so you take that in with every puff of a cigarette as well. If enough carbon monoxide binds to enough hemoglobin molecules, it will cause you to pass out and potentially die, because basically those hemoglobin molecules will no longer be able to bind to oxygen any longer. Okay, so that's the downsides to carbon monoxide. Now, the other thing about carbon monoxide too is it binds to hemoglobin about 60 times stronger than myoglobin. So myoglobin, so it won't even give up its let go of its hemoglobin for myoglobin. So myoglobin, it's about, like I said, about 60 times stronger at binding the myoglobin. So carbon monoxide is 60 times stronger at binding the myoglobin, about 230 to 238 times stronger than carbon dioxide. So bad stuff. Okay, let me clear this. And now let's move into exercise and altitude. So during exercise, there are a number of ventilation changes that happen that I'm sure many of you are aware of. So let's go ahead and take a look at what happens during exercise in order to increase the amount of breathing and ventilation in order to get more oxygen in and carbon dioxide out. So first of all, as all of you are aware, I'm sure, your ventilation becomes deeper and faster. And of course, this is to facilitate more oxygen coming in. If you're exercising, you're creating more carbon dioxide, and so you need to get rid of that carbon dioxide, so you get both things out of that: more oxygen in, more carbon dioxide out. Now, some of the other things that stimulate ventilation during exercise include the fact that your brain can detect when your muscles are moving. So as your muscles begin to move a whole bunch, that stimulates your cerebral cortex and your medulla, and that's basically what this neurogenic stimulation is. And your brain realizes, hey, if we're moving that much, we're going to need more oxygen and need to get rid of this carbon dioxide. So that increases your breathing rate as well. And then, of course, there's just the stimulation from the blood, like we were just talking about. The changes in the partial pressure of carbon dioxide in the blood, as well as the changes in pH, are going to trigger the chemoreceptors. And those chemoreceptors are going to feed back to the medulla saying, hey, our pH is getting low, our carbon dioxide levels are getting high, let's go ahead and increase breathing rate and depth. Now, if you recall, these chemoreceptors are in the aortic arch and also in the carotid bodies up in the neck. Now, in addition to changes during exercise, there are also changes that take place when you go to altitude. A typical thing that happens especially when you go to high altitude, right, is hypoxia. And so you should be familiar with this term. Hypoxia is just a condition where you have a low amount of oxygen in your blood. And this happens due to the pressure changes when you go to very high altitude, which I discussed in the prior lecture. So in order to offset hypoxia, there are some physiological changes that take place. And it's interesting, sometimes these physiological changes can actually mess with the carbon dioxide level. So you get this kind of imbalance of oxygen and carbon dioxide. So let's just take a look at this real quick. The first thing that happens when you go to altitude that you'll notice is you'll have ventilation changes. In other words, you will start breathing faster, and typically you're going to breathe deeper. And that's basically what these two bullet points are saying. Hyperventilation, so faster breathing. This is due to low oxygen levels. So in this case, your brain, so your medulla, is picking up that there's low oxygen, so it begins to pick up your breathing rate. So this is one of the cases where it's not carbon dioxide that's driving this ventilation change. It also causes you to breathe deeper, which means an increase in tidal volume. Remember, tidal volume is the depth and pace of your normal breathing. The next thing that happens is that your hemoglobin's affinity for oxygen changes. And this is typically due to an increase in production of 2,3-BPG, if you remember this. This molecule is created by the red blood cells, and what it does is it causes the red blood cells to give up more oxygen to the tissues. All right. It doesn't really affect how much oxygen they pick up at the lungs because you're already at 100% saturation typically. So it causes more oxygen to pop off at the tissues, and that is helpful. And then the third thing that changes is you wind up with an increase in hemoglobin production. And this is because the kidneys are going to detect low levels of oxygen and begin secreting the hormone EPO, or erythropoietin. And erythropoietin, if you recall, goes to the bone marrow and causes an increase in red blood cell production. And of course, the more red blood cells that you have, the more oxygen you're able to transport. So if we take a look at these changes on the next slide here, these are some things that you should be aware of as far as how quickly these three things happen. So here we have someone, so let me describe what's happening here. Here we have someone who goes to high altitude. So they go to high altitude, they're now experiencing a low partial pressure of oxygen in the atmospheric air around them, is what this is saying. They have an immediate change, and you've probably noticed this if you've ever gone up to go skiing and you go to a high elevation. What's going to happen immediately is you're going to start breathing deeper and harder. And so you can see here this hyperventilation that happens. All right. This is because the carotid bodies, as well as the aortic arch, the chemoreceptors there are detecting low oxygen levels. This will cause you to hyperventilate. Now, think about that. You're hyperventilating because you're low on oxygen, but that hyperventilation also leads to a decrease in your partial pressure of your carbon dioxide in your blood. So that's kind of interesting. You're taking care of one problem, which is your oxygen loading in your lungs, but you're kind of creating another one, which is respiratory alkalosis. Okay, so you get a decrease in your partial pressure of carbon dioxide that leads to respiratory alkalosis. and this actually increases the affinity of hemoglobin for oxygen. So you actually wind up, ironically, getting better oxygen loading in the lungs due to these changes. Even though it's causing an acidic change in your blood, which normally would not be good, here it does wind up being helpful, at least for loading oxygen in the lungs. All right, that happens immediately. Over the course of days, so if you spend a few days up in the mountains, what will happen then is your red blood cells will finally ramp up and start making 2,3-BPG or 2,3-DPG, same thing, right? This molecule will in turn cause a decrease in the affinity of hemoglobin for oxygen at the tissues. So let me be clear about that. Okay, so you have a decrease in hemoglobin affinity. This causes a greater unloading of oxygen at the tissues. So after about a week or so, you'll have both of these benefits kicking in. Then over the course of several weeks, so let's say you stay for a month at the top of the mountain, what will happen then is that your kidneys by then will have been making a bunch of erythropoietin, and then this erythropoietin will have had time to affect the red bone marrow, and that will begin to make more red blood cells. So it takes a while for this third one to kick in, especially. And this, of course, then increases the oxygen content in the blood because you have more red blood cells, which means you have more hemoglobin floating around in your blood. So basically, you kind of get this almost thickening of the blood due to having more red blood cells. So those are the three. They each take place separately, and it takes a while for the third one to kick in, that erythropoietin. Okay, so I think this is my final slide. Let's go ahead and, yeah, it is. Let's take a look here at the steps as far as what happens when you get to altitude. So this is basically just walking through the steps of what we just talked about. Okay, so first thing that we notice is that when we get to high altitude, we have a decrease in the partial pressure of oxygen in the atmosphere around us, right? This causes a partial pressure of carbon dioxide decrease in our blood due to hyperventilation. This in turn causes the oxyhemoglobin saturation levels to decrease due to the lower partial pressure of oxygen in the lungs. Now this is really more related to this, okay, not as much to this step. This is just an intermediate step that happens. Because of this, our ventilation then increases further, right, due to the low partial pressure of oxygen. And that leads to a total hemoglobin increase eventually due to erythropoietin, and that's because of the kidneys picking up on the lack of oxygen in the blood, which is called hypoxia. And then, of course, we also wind up with our 2,3-BPG increase as well, and this causes the decreased affinity of hemoglobin for oxygen. So basically, these all kind of stack on each other. And they all basically contribute to you being able to transport oxygen in your blood more efficiently. And with that, we are done with a short lecture for today. Thank you.